Okay, so we're taking a little bit of the region. We call that dA, right? dA, we've seen that before, and that's like a little rectangular chunk, dx, dy. And so we're considering how the vector. So in the vector field, there's vectors all around here, and so there's a change in the vector field as you change in dx. So as you go horizontally a little dx, the vector changes a little bit. As you go vertically a little across that element, dy, the vector changes a little bit. So the changes in these vectors, the changes in how these vectors create rate of change. So the first type of rate of change we're talking about is rotational rate of change. So as y changes, what components of the top and bottom vectors will create rotation? Do you remember? He says the horizontal components. And so that should just make sense. If I had like a piece of cardboard and I pinned it to the wall like this, how would you make it rotate? What would you do at top and bottom to make it rotate? Would you pull up and down? No, you'd pull sideways, right? To make it rotate. So that's why when it comes to those top and bottom vectors, we only care about what? The p components, right? P top and P bottom. So it's how much P changes for a change in Y. It's going to be that component of the rotational rate of change. How much P changes for a vertical change across your element. And then what about the ones on the sides? Again, green or pink, green or purple is going to make this thing turn about the center. The green ones or the purple ones? Or the two side vectors? Green ones, right? Green ones. Those are the Q components, right? The Q components. So Q right and Q left. Those components of the right and left vectors are going to contribute to this turning, right? Twisting. But the P components of right and left won't. So it's those four components, P top, P bottom, Q left, and Q right. So as X changes, whatever there's a change in Q, as X changes, is going to contribute to rotation. As Y changes, whatever change you have in P is going to contribute to rotation. So when we put that all together, we saw that the curl of F was Q, the partial of Q with respect to X, minus the partial of P with respect to Y. Because increasing P for a change in Y would cause clockwise rotation. So we have to take the opposite of it, because counterclockwise is positive. So this was the magnitude of the curl, we said. And then we said that curl is a vector. So what's the direction of the vector curl? If it's counterclockwise rotation, the direction would be? But what is the direction? It's going to be orthogonal to the plane of rotation, right? So that's going to be, if we're looking down on the xy plane, it's going to be in the z direction, right? Right-hand rule. If you're turning counterclockwise, direction of rotation as a single direction is orthogonal to the plane. So then that's why we said that the curl of F was qx minus pyk. All right, so now what about curl in R3? Well, curl in R3 is just the same thing, but three different times. So you've got rotation in the xy plane, rotation in the xz plane, and rotation in the yz plane, all happening at the same time. So you're gonna have contributions of all three. This will just be one of the three contributions. So let's just review again. We'll do it for the yz plane. So here, this is in the yz plane, but now, I don't know if you can see that, but now your little element is a dv element, okay? Well, that didn't show up very well, probably. So now we're looking at a dv element, and now specifically in that dv element, we're looking at the the YZ face of that. We've already done the XY face. So if you look, if you're on the top of this element looking down, everything from the last slide would be the same. It'd be all the same, and that would be the what? The rotation in the XY plane. The direction would be up now, right? In the Z direction. So now what about in the YZ plane? So again, as you have a change in Y, say change in Z first, what components of the top and bottom vectors, above and below, are going to contribute to twisting in the YZ plane? So here they are. So now I got green and red. Green and red. So as you change in Z, for a change in Z, for the top and bottom vectors, which components are going to contribute to rotation? Which ones? Okay, Harrison says the top and bottom vectors, the green ones are going to contribute to rotation, and for the sides, left and right, it would be the red. Agree with that? Okay, yeah, exactly. So it's the same thing, but now we're in the YZ plane. So then for a change in Z, that's up and down. Let's see. What's that? So if our vectors are P, Q, R now. So if we're looking at it this way, so P is the X component, then the Y component is Q, and the Z component is R. So these green vectors are actually, now these are Q's, right? Because these are the Y components of the vectors in the YZ plane, right? So it's going to be a change in Q. So Q is green. Q is green, R is red. Okay, so for a change in Z, it's going to be the change in Q for a change in Z. That's what's going to be rotational rate. And then for a change in Y, it's going to be a change in what? R, right? Change in R. So the same thing happens, and we're going to get the partial of R with respect to Y, or RY minus QZ, and that's going to be the rotation. And which direction will that be? It'll be RY minus QZ. And what direction will that be? In the X direction, coming out of the screen again. So now that coming out of the screen is the X direction. And so that'll be RY minus QZ I. So in R3, you're going to have 3 of these, right? You're going to have 3. We already did the QX minus PY times K. And then this would be the rotation in the YZ plane, which has a direction in the positive X direction. And then we'll have one more. Now, we're not going to talk through that one more, but we'll derive it here in a second. Okay, so since this is all about what rotation, this is really about cross product, right? So it's as much of F that causes, we're saying as much of F that causes rotation, right? And rotation gives us an orthogonal element. So we're going to use cross product. And so we can use the cross product algorithm on this kind of pseudo matrix, right? So you put I, J, and K in the first, and then we call this is called the gradient operator. It's not values, it's telling you to do something. Take the gradient. So that's our gradient operator, okay? Normally we set up a matrix and we have 9 values, right? Well, now you have I, J, K vectors, and then you have this operator, which is like telling you to do something, and then P, Q, and R is our components of our vector field. But to find the curl, we're going to do the cross product. We're going to do the same algorithm of the cross product that we did when we were just finding the cross product of two vectors. Okay, so remember what that was? So the I component, what we'll have, will go down to the right this way, and so we'll take the partial of y, partial of r with respect to y. But then also so here's another I here. We'll go down this way and we'll subtract, right? Minus what? Q with respect to z, and that'll be our I component. And then, well, j component. Positive would be what? P with respect to z, minus, going this way, down this way, Q with respect to x. And then finally, the one we're familiar with, Q with respect to x. Did I get that right? P with respect to z minus r with respect to x. All right. And then the one that we're most familiar with, qx minus py, z. Okay. So when you're computing the curl of a vector field, this formula holds, but I just recommend that you just work it out through the matrix method each time, rather than trying to remember or look up this formula every time. Just put your vector field, put your components of your vector field here, and work through the cross product algorithm to derive the curl vector field. So this is the curl. In the three different planes, xy, yz, xz plane, you have contributions of rotation due to the vector field. Okay? And that's a new vector field. Notice this is a new vector field. The curl of f is a new vector field which is like representing the rotational rate of change of f. So the magnitude of the rate would be the magnitude of the curl, and the direction of the curl would be orthogonal to the plane of rotation. So once you add all these three components together, you'll get a particular direction of a vector. So it may be slanted in space. That means that your rotation is in a particular the plane orthogonal to that. But that's made up of the three components orthogonal to the coordinate planes. Okay, really important point here. So curl is a function. Rotational rate, what? It's a pointwise phenomenon. What does that mean? It means it varies depending on the specific location in the field. So you have a particular curl vector at every point in your field. And that's the rotational rate of change at that point. Super important. Curl is a pointwise phenomenon. Given every point, there's this associated curl with that point, and then all those curls together make the function. Okay, so let's look at this. So here's the vector field. So this is a vector field in just the xy plane. Okay, this is just the xy plane. So what about the curl? Is the curl positive or negative? Is the curl positive or negative? Positive. Why do you say positive? Rotating counterclockwise. Okay, let's take a look. So let's look at a point. Let's analyze this here a little bit. Let's look at a point right So at that point, we can look at the vectors kind of surrounding it, kind of what we did to derive curl. And so I want to look at, if I'm looking to the vectors left and right, am I interested in their horizontal or vertical components? The ones that are left and right at that point. Vertical, right? So there's the one to the left of it. And there's the one to the right. So looking at those two vectors and their relative size, do they indicate clockwise rotation or counterclockwise rotation? So the one on the left is larger pointing up than the one on the right is pointing up. So would that make it turn counterclockwise or clockwise? You should be thinking clockwise. Okay, well that's only half the picture, right? So looking at the vectors to the left and right, it seems to indicate clockwise rotation. Okay, how about above and below? So as I go up from here, are the vectors getting bigger, the components getting larger or smaller going up? Smaller. So here the one below is bigger to the left than the one above is to the left. Does that indicate clockwise or counterclockwise rotation? Also clockwise. So both the vectors to the left and right and the vectors above and below are indicating clockwise rotation. Do you see it? So I ask you again. Well, at least at this point, is the curl positive or negative? It's negative, right? It's negative because looking at this point, when we analyzed the vectors, it showed that our conclusion was clockwise rotation. But I thought you said the curl was positive. Yeah, Lane.
I was thinking that, like, I can't really tell the unit because it's like the second tick mark on 0.2 and then also 0.2 right in the center where you have the really large vectors.
Mm-hmm.
I was thinking that there, the curl would be positive. But, so that's why I was thinking why the whole thing would be positive. Looks like that.
But the reason you thought the whole thing was positive because you just looked at the big whirlpool, right? Right. Okay. So maybe there's somewhere we could do the same little analysis and you'd also get positive. But I think for the most part, most points you pick in this vector field, you're going to end up happening what's going to end up happening is what just happened, and that is if you just analyze it at a point, you're going to get clockwise rotation. So what is the moral of the story? It's what I just said before we did this little exercise, which is what? Curl is a pointwise phenomenon. It's not a global phenomenon. So here we are in this counterclockwise rotating whirlpool, but in fact the curl is negative. So it's a good way to think of this is think of this as like a whirlpool, like a water flow field, and you put a little flywheel in there. When you first answered the question, is the curl negative or positive, you were thinking about what about the flywheel?
Where would I travel?
How it travels, right? How it travels. And it's going to travel around counterclockwise. But what should we really be thinking about this flywheel? How it spins, right? How that spins, because that's the pointwise phenomenon. And how does it spin? It spins this way. So as it travels, yes, in a big counterclockwise circle, what's important for curl is how is it spinning? And it's spinning clockwise. So the curl is negative. Yeah.
So it's like rotating like this, but also turning like
Yes, yeah. So just think of it as a ride in an amusement park, right? It's just, you got this big platform going around like this, but then all the individual cars spin the other way. And how the cars are spinning, that's what the curl is. Okay, that's pretty cool. So now, if I were to ask you the same question, maybe. Oh, where'd you go? Let's back in this one. If I were to ask you the same question about this one, I said, okay, let's look at this. Is the curl, sorry, too many windows open. It's my life story. Is the curl positive or negative? What's the right answer? Is the curl positive or negative?
Where? That's where.
Who knows? Yes, the whole thing is again rotating counterclockwise. But we have to do more to answer that question. Just by glancing at it, you can't tell. So this time I'm going to show you what the vector field is, and I want you to use their algorithm to calculate the curl, and then from your calculation of the curl, we'll make a decision. So here's this vector field. It is negative y over x squared, 1 over x, 0. That's what the vector field I'm showing you. And so you can use the algorithm to find curl of f. While I take attendance. So now we're algebraically computing this new vector field, which is the curl or the rotational rate of change for that field. Go. What did you get for the x component? Or the p? 0. Okay. Y component? So let's see. With respect to z, with respect to x, 0. Okay. And then how about, so what about, now, that should have been expected. Why? Because this field is in the xy plane. So all the rotation, if there's any rotation, all the rotation's in the z direction. So we could have predicted that before we even started. Does that make sense? Because this is an xy vector field. The only possible rotation could be in the z direction. So the math makes that check out, but we could have predicted that. Okay, so now finally, with respect to z. So this with respect to y, let's go this way first. Let's see, with respect to x. So what's that with respect to x? Negative x to the negative 2. And then going this way, it'd be minus a negative, so plus the rate of change with respect to y. X to the negative 2. Which is? So the curl is? So what does that mean about this? So you put the flywheel in there, or what happens? It'll just move around without spinning, right? And then, so that means everywhere in this vector field, the curl is 0. Okay, so this was, what is this? This is our qx minus py, right? So when qx minus py is 0, what does that mean? We've talked about that before. Qx minus py is 0, that means qx equals py. It's a gradient field, right? So if qx, that means qx equals py. That's Clairaut's theorem. Conclusion is conservative. And we can extend that to R3 vector fields. If you, in an R3 vector field, if you get all 3 components of the curl to be 0, then that's a conservative vector field. And now we know something more about conservative vector fields. What's an added feature that we know about conservative vector fields related to this? Yeah, so that's the curl is 0, and that what we say there is they're irrotational. So the curl equals 0, and that's called irrotational. Conservative vector fields are irrotational. There's, at any point in a conservative vector field, there's no tendency of rotation at all. And so your qx minus py and your whatever the other ones are, px minus rz and Rx minus QZ or whatever it is are all 0. Okay, any questions on this example? Yes, please, sorry.
So if QX minus PY is the only part that determines if the vector field is conservative, then why does the I and J components also?
Okay, so this is strictly a R2 vector field to start with. So in an R3 vector field, in a truly three-dimensional vector field, when all 3 components are 0, that's not none of those being 0 is guaranteed. In an XY plane vector field, these 2 are guaranteed to be 0 always. Okay, so in an R3 vector field, you could have, none of those are guaranteed to be 0. If they all are 0, then it's a conservative irrotational vector field.
So it's not necessarily have to be 0 for I and J in the 3D.
Most of the time it won't be. The reason it is here is because this is a 2D vector field, and the only plane of rotation is the plane of xy, which means all the rotation would be in the z direction. Does that make sense? But now, so that taking this a step further to a 3-dimensional vector field, yeah, you definitely will not have any components to be 0 necessarily. Most of the time they won't be. If all 3 are 0, then it's an irrotational conservative vector field. It's a conservative vector field, therefore it's irrotational. Other questions? Yes, please.
So when you say irrotational,
Yeah.
if I had a point somewhere to the right of the origin and I moved all the way around, like kind of following the vector field,
Yeah.
would it not rotate with respect to the origin, or would it just not rotate at all? So like if my pencil was like this, and it would just stay pointing up the whole time? See what I'm saying?
Yes.
It would. Okay.
Yeah, it's kind of weird. What does it mean if it's moving in a circle? What does it mean to not rotate? Does that mean that the top point always stays at the top, or does that mean that the top point always stays furthest away from the origin? Which I'm actually not sure.
I think it's the second one. I think it's the origin.
Yeah, I think I agree too. So yeah, so if you have the flywheel, and you mark the point right here, say at the top, or say, so if that point always stayed at the top, would that flywheel be turning? I think the answer is yes.
Yeah.
It's because it's moving this way right now. So for it not to turn would mean that point would stay furthest from the origin. Yeah. Did that answer it? Yeah. So I think it's kind of like Mercury? The planet Mercury. One side of it is always facing the sun, and the other side is always in the shadow. That would be irrotational. So
With respect to
yeah. Okay. Other questions? So let's talk about the other kind of rate of change, which is a lot easier. Phew. Got the hard one out of the way first. So the other one is called divergence. And this is the rate of change that's regarding expansion or contraction at every point. It's a pointwise expansion or contraction rate. A lot easier. We're going to take our same little element, our same vectors, the same components, and now we're going to ask, if you changed y a little bit, what would contribute to expansion or contraction? Purple or green? If you change y a little bit. If you change y. So if you change this way, the change in which component is going to contribute to expansion or contraction? Purple or green? Green. And if you change x a little bit, now you're talking about the purple vectors. So as x changes, so for a change in x, we want the change in p, the horizontal components. So that's the partial of p with respect to x. And as y changes, we want the change, we were looking at the change of q, or the vertical components, for a change in y. So now we're talking about p with the partial of p with respect to x, and the partial of q with respect to y, and then those are both going to contribute to overall expansion or contraction at this point. So the total rate of expansion is just going to be the sum. You're just going to add them all up. You're going to have a contribution from p with respect to x, q with respect to y, and r with respect to z. Yeah?
Is that just like the acceleration in vector fields?
Not quite. Because that's more like a second derivative, right? This is still a first derivative.
Yeah. But like, if you're looking at a gradient field, or I guess it's the acceleration of the original function. Kind of.
It's pointwise, so it's not really acceleration. It's like pointwise tendency of expansion or contraction. Acceleration is kind of like second derivative.
Yeah, but
This is
isn't
still-
the gradient field already the first derivative?
No,
It's not?
no. So what we said was, if your vector field is a gradient field, then yes, it's like the first derivative of
Oh,
f.
okay, so
But now we're just talking about vector fields in general as the baseline function. And so then we're looking at the two derivatives, the curl derivative and the divergence derivative. So this is still first derivative. So for a change in y then, we're looking at the y component. So we want as much of these vectors are as in the direction of change. And then in the x direction, we want we want as much of those vectors as in the direction of change. So what's that going to be a matter of with our gradient operator? So it'll be what? It'll be dot product this time now. So it's going to be, the divergence is going to be the dot product of the gradient operator with the vector field. A lot easier, right? Super easy. You just take the partial of the p component with respect to x, q with respect to y, r with respect to z, and add them up. And again, that should make sense because, say, in the x direction, for a change in x, it's how the x component changes. So we want as much of those vectors in the x direction for a change in x. P with respect to x. As we change y, we want as much of those vectors as in the vertical direction. Q with respect to y. And then you have the z component as well. So let's go back and look at that one with the second one we looked at. Oops. Oh, hello. Let's just predict. We're going to eyeball and predict, okay? So here we are over here. So right here. So now if we're talking about divergence, then in the x direction, we're looking at x components. And here's how you analyze divergence. You look at the direction that you're moving, and you say, so as you're moving, so in the x direction, we move into the left. Is that right? Because the components are facing left. And as you move left, is there a tendency of expansion to the left or contraction to the left? If the vectors are getting longer as you move left, expansion, positive divergence. What about going up? So going up, this vector here, this vector here, this vector here. What about going up? Looks like they're staying constant. So like in the y direction, it looks like the divergence is kind of zero-ish, right? Zero-ish. So in the x direction, positive. In the y direction, zero-ish. Conclusion here, divergence is positive. Okay, but let's go over here. Let's look at this point right here. So again, movement is to the left, and as we move to the left, what's happening to the x components of the vectors? Smaller. So we're moving to the left, and the vectors are getting smaller. Tendency of expansion or contraction? Contraction. What about up and down? Zero-ish. What about that divergence over here in quadrant 2? Looks like it's negative, because we have a tendency of contraction horizontally, and kind of vertically looks like it's staying the same. Okay, down here. Horizontally. We're moving which direction? Right, and as we're moving right, expansion to the right. Expansion to the right. And what about vertically? It's like holding steady. Divergence over here. Finally, moving to the which way? Right. Moving to the right, the vectors are getting smaller. Tendency of expansion or contraction? Contraction. Again, vertically, looks like they're staying the same. Prediction? Okay. Prove that result that we just found. That the divergence is positive in the first quadrant, negative in second, positive in third, negative in fourth. Prove it mathematically. Prove it mathematically.
So like,
Right.
but when you're in the negative x, you have the side. And that's how you get.
What'd you get?
Is that the matter of this original picture? Only working with this divergence.
2y x negative 3
Then we just know that if they're both positive,
plus 0 plus 0.
so the first quadrant, it'd be a
Oh, okay. And then since we have x as a negative.
yeah.
Okay, so did you get 2y over x cubed as the divergence?
Yes.
And does that prove it? In the first quadrant, what do you have for y and x?
Positive.
Both are positive, so divergence is 2y over x cubed will be positive since both x and y are positive. Second quadrant. X is negative, y is positive. Therefore, 2y over x cubed, negative, etc., right? So looking in those quadrants, we know what the relative signs are. Now, there's just one more point. How is the divergence of f different than the curl as a function? So they're both functions that give the rate of change of f. But there's a big difference between the curl of f and the divergence of f. Yeah? This is a scalar function, right? There's no direction associated with divergence. With curl, there's direction associated, right? Orthogonal to the plane of rotation. But with divergence, dot product just gives you a scalar value. Now that value can change at different places, but it's still just a value without direction, either tendency of expansion or contraction without direction. So it ends up being a scalar function, whereas curl is a vector function.